Hey there, everybody. The purpose of this video is to walk you through a solution to exercise 4.15.12 in collaborative statistics. It deals with the binomial distribution of, it looks like, a local high school picking 60 seniors and checking how many of them participate in after-school sports all 4 years. Okay, so you know it's binomial because number one, you got a fixed number of trials. They've selected 60. Number two, it's given you a percentage of 8% of students at a local high school participate. Okay, so you've got a fixed number of students and you've got a fixed probability. The only thing you have to be concerned about is the population size you're drawing from. We're going to assume we're sampling independently. I'm assuming when they say a group of 60 seniors, they mean a group of 60 different seniors. And in looking at the draw, taking one senior out of however many there are, and then taking another senior out of however many there are, we want to make sure that you're not taking so many seniors out that you're actually affecting this 8% as your sample is drawn. For example, suppose there's only 100 seniors in the entire class. Well, if you're taking 60 out of that class, you've got a bit of an issue because once you've taken 30 of them out, you've removed 30% of the population. Well, removing 30% of the population is a bit of an issue because now the 8% might not necessarily maintain. We're going to assume that the senior class is large enough so that drawing 60 of them is not going to be a huge deal. Now, just as a caveat, if it were, you'd have to use something called the hypergeometric distribution, which I'm not sure if this book has anything on. I'm not going to expect you to have anything on it, but just make sure we're going to make the assumption that there's enough seniors so that the 8% is not damaged too greatly if we draw 60. Anyway, the book first wants us, I'm going to scroll up here real quick, it wants us to define the random variable x, list the values of x, and give the distribution of x. We're going to do all that at once. We already did one, actually. Giving the random variable x is, they've told us that, of interest is the number that participated in after-school sports. Oops, I'm trying to highlight it here. There it is. The number that participated in after-school sports all 4 years of high school. That can take on the values of 0 through 60. So that's our random variable. B and C define the values x can have and give the distribution. We can do that on our TI, which I've already done for you here. I ran the dist fill program, and we've got the entire distribution right here. So you've got all the random variables over there in list 1, and you've got all their probability values over here in list 2. Okay. So now it asks us a number of questions based off that distribution. So first, how many seniors are expected to have participated? Expected. So out of 60, how many would you have expected? Well, that's the average of the distribution. So we'll go to 1var stats. We'll do it this way first, then we'll talk about it a different way. L1, L2. On average, 4.8 of the 60. Now, 4.8 of the 60, you might ask yourself, that sounds kind of familiar, because you can put 8% and 60 together to get 4.8. 8% of 60 is exactly 4.8. Well, 4.88. Oh, excuse me, I typed the wrong number. 8% of 60 is 4.8. And there you go. So that's a shortcut for the binomial. You can take the probability of success times the sample size, and you get the average number of successes. But you can also just run 1var stats, like we've been doing for weeks now. So there's part D for you. Based on numerical values, here's part E. Would you be surprised if none of the seniors participated in justifying mathematically? Well, when they say, would you be surprised, that makes me think of, would that be an unusual event, which would surprise someone, right? So up here, in L1, 0, in L2, its probability, there's less than a 1% chance that no seniors will play after-school sports in all 4 years. So basically what that means is fewer than 1 in 100 seniors should play sports all 4 years. Fewer than 1 in 100. According to this, it's about 7 in 1,000. So would you be surprised? Yeah, by mathematical definition, yes, because it's less than 5% the cutoff. It's a very, very rare event. I would be more surprised if we're up here in the distribution. Let me slide down here a little. I guess I got to click them all. I'd be more surprised down here, like if we had 24, because that's 0.000000008. But yeah, for 0, I guess I would be surprised because it's a very low probability. So there's the answer to E right there. And an F, based on numerical values, is it more likely that 4 or 5 of the seniors participated in after-school sports? This is just kind of fun. I've lost the TI now for a moment. We won't see it, but we can kind of think about it. If we know the average is 4.8, 4.8 is closer to 5 than it is to 4. So you know numerically the probability of 5 is going to be, and 4, it's going to split the probability of 4 and 5. So the average being 4.8, 4 and 5 are both around the same likelihood, although you can see the chance of 5 is slightly lower than the chance of 4. So basically, when it says, is it more likely that 4 or 5 of the seniors participated, strictly numerically, it's more likely that 4 participated than 5 participated. Strictly likely. But essentially, those are the two modes of the distribution, because roughly, if you look at this, 37% of the results are going to fall between 4 and 5. So I guess that's what we're getting at there. All right, so I hope that helped, and yeah, binomial distribution, we like it a lot. See ya.